What is going on, everybody? It's Mr. Custom. I'm back in the physics conference room. Today I'm setting up a lab. I have got our parallel RC circuit lab. What that means is that I've got three light bulbs organized in parallel with each other with the battery, and I have got a capacitor in series with one of those in one of the branches. So it's going to be a little messy on the tabletop. So let's look at the schematic first. I've got a battery. That battery is set to 5 volts. And then I've got 3 light bulbs all in parallel with each other, but that third branch, notice that third branch has got a capacitor in it. It's got a 1 farad capacitor in it. Let's see what happens when I turn this circuit on. I've got 1 light bulb here, you can see. I've got 1 light bulb here. I've got the third light bulb here, so you can see all 3 light bulbs. You can see the capacitor. This light bulb here in particular is the one that's in series with the capacitor. It's in the same branch. Let's check out and see what happens. Power's on, boom. 1, 2, 3, all bulbs are lit. Every branch is receiving current right now. We can compare the capacitor bulb, that third branch, with a more with the non-capacitor branch. You can kind of see that. And if I go side by side on these guys, what you can start to see, I think, hopefully, we'll see if we're getting charging on the capacitor. There we go. You'll start to see this is starting to dim. So as the capacitor charges, as charge flows through here, you'll notice this is dimming. Now, if you recall, it's dimming a lot slower than it did at 5 volts in our series lab, which is curious that it's doing that. I mean, I wonder what that means in terms of the different junctions and the amount of electrons or charge that does build up on the capacitor. But, all right, now we're here. This bulb is out. You can see this bulb is still lit. This bulb is still lit, and they're actually getting pretty warm. Now, let's watch and see what happens. I'm going to go ahead and turn this battery off. I'm not going to change any wires, but I turn it off. This battery goes on, and these bulbs are dim, very, very dim, but they are still on. Again, battery's off. I haven't changed any wires, but all 3 light bulbs are still on. The one connected in series to the capacitor is on, dimming very slowly. And the 2 other ones that are in other branches were much, much, much dimmer. All right, let's take some data, right? Let's take some first data. Let's go ahead and look at what happens initially. I want to know what happens to the resistance as we go from initial to final, right? What happens here, right? Like, what happens to these things as we go from initial to a steady state? Let's go steady state. So the first things first, we know that the resistors aren't going to change. The resistance of the light bulb is not going to change. It's going to stay the same. Right? That's what it's going to do in both those bulbs. Let's go ahead and look at what the current does and what the potential does at each of these things as we go from steady state or from initial conditions to steady state. Now, in terms of voltage, before we take this measurement, what I want us to think about is that in our loop rule, the battery doesn't change. The battery is cranked up to 5 volts the whole time. So in this loop, there's only one resistor, and it's the light bulb. So that being the only loop means the voltage at that first one should be 5 volts the whole time. And at resistor 2, it's still a loop. That resistor also should have a potential difference of 5 volts the whole time. Now at resistance 3, we notice that bulb actually goes out. So as we go from initial conditions to steady state, if it goes out, we know it's not receiving any current. We know it's not receiving any potential. Well, if it's not receiving any potential, it's not receiving any current, we would need to treat that resistor as also 0, okay? So we're seeing that there. Now, what I want to do, I want to check and see what is the total current across this circuit. Let's go ahead and check out the total current across the circuit. I'm going to go ahead and grab my power or my multimeter. I'm going to plug it in. I'm going to get over here to amps or my amperage, and let's go ahead and check out total. To find total, all I'm going to do is break the circuit, and I'm going to plug it in to the battery right here. Let's go bang. Make sure the current or charge flows through my multimeter. So I'm plugged in right now. You can see it. This is measuring total current. Let's watch what happens. As it goes on, total current's at about 0.8. And as we go, we can look at our indicating light bulb over here. If I can flip it around. This indicating light bulb is going to get dimmer. As it gets dimmer and dimmer and dimmer, where I'm watching the current go down. Again, we're reaching a steady state. So initial conditions, steady state. We're on our way to a steady state. Steady state means the current's going to stop changing at some point once we're totally charged. So what do you notice here? I notice that the total current drops. Let's see if it keeps going. This looks like it's out. And we'll see if it keeps going. It might not be totally out yet. We may not be totally charged. But it looks like we're going to stay steady. Like this is our steady state. At a steady state, what did you notice about total current? Well, clearly, total current is decreasing. This goes down as we go and charge this. And that kind of makes sense. Because if I charge this capacitor, this resistor goes away. I'm removing a parallel resistor. By removing the parallel resistor, I should be increasing the overall resistance. I had 3 resistors in series. Now I have 2. I know that adding resistors in parallel decreases the resistance. So if I take one away, I should increase the resistance. If I increase the resistance and I keep the voltage across everything the same, well, guess what? I should see a decrease in current. And I do. So that makes sense to me. Okay, I get it. I see a decrease in current. But now, because I'm decreasing current there, in that branch, what does that mean for the current in branch 1 and branch 2? Let's try that. So let's discharge this whole thing. Let's unplug this, let's discharge it. We'll track this here. I don't need to worry about keeping it plugged in or not plugged in. We're going to go ahead and disconnect. We're going to have to reconnect to the battery and let it charge back up. Where is this wire going? That is connected there. This goes here. All right, let's get the multimeter out of here. The multimeter is free to go. Now, let's go check what happens in this branch right here. So we're going to go ahead and in this branch, in the second branch, we'll go connect it here. Come on, current in. Boom, boom. Okay, so now I have got my multimeter, my ammeter, because I'm measuring current at this point. I've got it plugged in right here. Okay, see that? So I'm going to go ahead and check to see what happens to the current. Do I? No, I don't. I do not have it there. Take this all out. Hang on. Let's go ahead and move this to right here. Boom. Let's put this in the common ground. We can put this right here, and then we can put this one actually right here. That'll do it. Okay, now we're there. Now we got it plugged in right where I said. We got it plugged in basically in branch 2. We're going to measure the current going into that light bulb in branch 2 once I turn this thing on. So let's go ahead and check here. Boom, that's on. Here's my indicating light bulb. It was 0.26. Let's see what happens to that current. This is already getting dimmer. This is almost out. Notice the current is not changing. So that kind of makes some sense, right? Like the battery, the resistance in the light bulb doesn't change. The voltage across that loop doesn't change. And so the current doesn't change. So why does the overall current decrease? Well, the only reason the overall current decreases is because we lose this third branch. That's the reason why. So don't be fooled. Don't think that, oh, these must also change. They don't. The current in these branches remain the same. So I see same resistance, same current, same voltage in these 2 parallel branches. However, in the third branch, notice that the voltage across the resistor goes to 0, the current to the resistor goes to 0, and the resistance must be treated as 0. So what does that mean for the capacitor? Well, the capacitor at a steady state, as we go from initial to a steady state, the voltage, the current, and the resistance. Well, again, there's never really current flowing through that, so we won't talk about that. There's definitely no resistance talking about there, but initially we have 0 voltage across it, and by the time we reach a steady state, we now have 5 volts across that capacitor. So we're seeing this trade-off between the resistor losing current through it, slowing down, current starts to stop, that voltage goes from the resistor to the capacitor. And again, after one time constant, we'd call it 63.2% of the total voltage stored in the capacitor. So hopefully we understand that resistors in parallel and having a capacitor in series, one of them, this is kind of the lab that we did. We hopefully have some understanding of how these things change from a initial condition to a steady state. If you need more practice, go see the practice problems video that follows this video. Otherwise, if you have questions, you ask me in class. You send me an email or drop me a comment. Yeah, until next time. See ya.